Hello and welcome back. So this is part two of your Module 5 lecture. This is definitely the back half of what we're talking about this week. So we're talking about regression assumptions, how to assess them, uh, and what to do when those assumptions might not be good to make, right? When there might be problems with those assumptions. So the last part of this lecture, we're going to focus on two things. We're going to talk about how to look for what are called regression outliers, and also how to sort of use bootstrapping, a statistical technique to sort of check whether or not the violation of assumptions might be an issue, to kind of address those issues with assumptions. So let's start with this concept of regression outliers. So we've previously talked about and you've talked about, I'm sure, in EDUS 608 or a previous stats class, how to identify outliers for a single variable. Remember we made those box plots in Stata or R, and the top whisker, right, is the max, and the bottom is the min, and then any points that are indicated are suggested as outliers. So that's how you look for outliers in a univariate situation. And that's helpful. But a lot of times we actually want to think about outliers in a more broad way. We want to know if certain observations are outliers in terms of their influence on our results, on our actual regression, taking into account multiple variables at the same time. So one way to think about this is, if I think, let's say, for example, we were studying that situation that we talked about in the previous module, where we studied sleep, right? So we looked at sleep in month 1, month 2, month 3, and month 4. Well, let's say you have somebody in your sample who just wasn't sleeping at all, right? So they would look like, if we looked at month 1 sleep and we try to find that person on the plot, they're probably going to be an outlier at the bottom with a very low amount of sleep. But maybe whatever treatment we were doing with that group actually worked for that person, and they actually gained a little bit of sleep. Now, not a lot, but they actually had some positive growth in sleep, to the point where they're still outliers, but they're not as extreme going from month 1 to month 2 to month 3. The issue is you might look at that plot and say, oh, that person's an outlier, when they're actually not. They're functioning according to what you might expect given the model. They're improving slightly over time. They just started at a lower point. So that's the difference really between a univariate outlier and a model outlier or a regression outlier. The regression outliers are the ones that we're really interested in the most. So there are two ways to do this. One is to look at a histogram of standardized residuals and kind of see if any observations are sort of way outside or beyond the bounds of, like, negative 2.5 or 2.5. We learned this in the previous, not last week, but in the previous video, sort of looking at that. I'd say that is an inexact approach because sometimes it's hard to know, excluding someone from your sample is a big deal, and excluding someone based just on that criteria can be a tough call. Another kind of more rigorous way that I highly recommend is to calculate what's called a Cook's distance for each observation, and then analyze your results with and without those people included in your sample. So let's get into that a little bit. So this is just a little visual of what happens with regression outliers. So here we have, this is just a nice figure from Andy Field. I think a lot of his visuals are really helpful. So he's got this graph of album sales and advertising budget. So this is a scatter plot, right, with two continuous variables. So we're basically looking at each one of these each one of these is an album. It's hard to think what albums are these days, right? Everything's on, some kind of streamer. But anyway, so each one is an album. And then we're looking at the budget that was included to advertise the album and its sales. And roughly we see this sort of positive relationship. represented by the green dots here. And then if we fit a line, you know, that's a simple linear regression. And basically, the more you get, the more you advertise, the more you sell. That's the example here. So what happens then? So let's assume our first model just includes these green dots. Imagine we have a case like this that is included in our sample. So here we have an album that has a huge advertising budget and very few album sales. So this would be like maybe a really popular band that got a little bit older and they spent a lot of money and they just kind of fell out of popularity, whatever it is. I shouldn't make up stories. I feel like U2 is an example here, but no, that's not good. That's not good. I shouldn't cast any shade at U2. So here's the outlier. So there's our outlier. So what actually happens is if we include this data point in our regression model, this one point actually pulls the whole regression line down. It actually makes the relationship between sales and budget less positive by a significant amount. And that is the classic definition of a regression outlier. So that a single data point. Now imagine if I deleted, for example, this data point or this data point or this data point, that line, that green line wouldn't change very much. But if this thing was included or wasn't, it's going to have a huge effect on our results. And those are the things we're trying to get with the regression outlier. So the statistic that tells us this is called the Cook's distance. And it's basically a measure of influence of a single case on your whole model. And it's a more precise way to measure those influential cases that you think are biasing your results. So what Cook's distance is in a kind of conceptual, just in words, right? What Cook's distance is telling you, if I deleted this one observation from my model and then reran the results, by how much would my predicted values change? Would my estimates change? So that's the question. So if I have 100 data points in my sample, 100 albums, and I deleted one of those albums, how much would my predicted values change? And the fancy version, of course, is a formula. So Cook's distance is usually represented by this capital D, and it's basically the sum of these model comparisons. So Yj minus Yj sub I. So these are basically the comparing the model itself with a data point included and the model itself without the data included. And so we have observation I and model J. So here's model J with I and model J without I. And then you have a number of predictors and a variance. So that's the formula. We don't actually need to know the formula because it's well established and it's calculated for us. But the big idea is the larger that Cook's distance, the more influence that individual observation has on your model. And so if you have certain observations that are causing you trouble, the recommendation is to remove those observations and rerun your estimates and see. Ideally, every data point has only a small influence on your results. But if there are data points that are influential, those D values, those Cook's distances, are going to be really big. All right, so what counts as a big Cook's distance? Well, as the saying goes, ask 4 statisticians and you'll get 5 different answers. So basically there are 3 sort of imperfect thresholds that we're looking at. First of all, if you have any values in your data set that are larger than 1, those are definitely cause for concern. So if any individual observation has a Cook's value greater than 1, it is definitely impacting your results and should probably be removed. This, however, is probably too conservative of a threshold. There probably are Cook's values less than 1 that might actually still be an issue. And so another threshold that was proposed a while ago is to take your sample size, n, and divide 4 divided by n. And that is a good threshold. This is actually probably too liberal. So you're probably going to kick out too many people according to that threshold. So it's somewhere in between, right? You think of the Goldilocks example, right? Not too hot, not too cold is probably the best approach. Another approach, which is more subjective, is to use a scatter plot and just look for patterns. Are there certain data points that have much larger Cook's distance values than the others? And what happens if those are removed? And I'm a big fan of that approach, actually. I think it works pretty well. So this is an example. This goes back to EDUS 608 days. So here we have, we were running some model where we were predicting like test scores based on the state and how much is spent on education. And then you have, so each one of these dots here represents a state. So the contribution, the sort of Cook's distance associated with each state. And so if we were evaluating this and looking for outliers, well, none of the states have a Cook's value above 1. The highest value is like 0.12. 2 states are above 0.08, and that would be the 4 over n threshold. So 4 divided by 50 is 0.08. So New Hampshire and North Dakota are both clearly above that. And those same 2 states also have significantly larger values than the rest. So if you draw a line going across here, those 2 states sort of stick out more than the others. So if you had to think about removing 2 states, it would probably be those 2. So you might try removing North Dakota and New Hampshire, rerunning your analysis, and comparing the results. Hopefully it doesn't change very much, right? Because if you're doing an analysis of 50 states, you want all 50 states to be included. But this is basically saying these are perhaps too influential of impact on your model. All right, a couple other assumptions, or sort of assumptions and tools to check. Multicollinearity is an important one. So again, multicollinearity, I talked about this a bit in part 1. That just means that your predictors in a model are probably too highly correlated with themselves and also with your outcome. And what happens is this biases estimates and can also limit generalizability. One thing you can do just as a quick check on this is to do a correlation analysis of all your predictors. And hopefully no correlations should be above a 0.8 or a 0.9. And here's a visual of what this looks like when you have considerable collinearity. So we have here 2 situations. So the Venn diagrams on the left, this is a situation where you have what's called modest collinearity. So this is fine. This is sort of a normally functioning model. The model on the right is a model where we've got issues because we essentially have considerable collinearity between the 2 variables. So our outcome here is y, is this yellow circle, and our predictors are x and w. Those are our 2 predictors here. And we can see how they all overlap. So blue, right, that is the unique contribution of variable x on our outcome, and green is the unique contribution of variable w on our outcome. And red is the portion which they share. So this is the collinear portion. And same here, blue, unique contribution of x, green, unique contribution of w, red, shared portion. And notice that is much larger. So here we have only sort of a modest correlation between x and w. So we have an estimate of that, but we also have plenty of room to get an estimate of the blue and green portions of our pie. Here we have a strong correlation between x and w, and so the unique contributions of x and w are just these little slivers of blue and green, and that is a visual demonstration of multicollinearity. It means it's very hard to get a good estimate of that little piece when so much of the variability is shared between the 2 variables. The easiest way to assess this is actually with a statistic as opposed to a Venn diagram. And so there's this statistic called the variance inflation factor, VIF, and it can be easily calculated in both Stata and R. And Stata, the command is estat_VIF, and that's after you run your model. And in R, there's a package called CAR, Companion to Applied Regression, and it has a very nice function called VIF, which does the same thing. So you basically run this function, and you're going to get VIF estimates for each of your predictors. And what you're looking for is that for each of your predictors, the VIF value should be less than 10, absolutely, but ideally even less than 5. So in this case, right, this is our video games example. We look great over here. Callus and video games are not collinear at all. VIF value is 1. Over here, this is our example from this week. This is our skewed data set. Here, X1 looks good. X2 and X3 look like there might start to be a problem, right? Both of these have values above 5. So this is when you start to perk up and think, that's not so great if you have a bunch of variables with VIF values above 5. All right, so the recommendation is when you have multicollinearity, it usually means you're getting competing signal from two variables, right? And so the solution is usually to drop one of those variables and rerun your model. That's usually what the recommendation is. Because essentially you're getting the same information, redundant information, and it's actually biasing or making it difficult to estimate the standard errors for those individual variables. So that's the recommendation, would be to drop a variable, one of the variables, and then rerun is typically the solution. All right, so those are the assumptions. I know it seems like a lot of things to pay attention to, but typically, you don't go through all of these assumption checks every time you run a model. You would want to do this with any sort of final model, any model that you think sort of represents what you want to study. Maybe it's your final model for a paper or dissertation. That's when you'd start to sit down and say, okay, I need to really dig in and make sure that I've met all these assumptions. And sometimes you can't, right? You can't meet all the assumptions. And so there's this procedure called bootstrapping, which is a really relatively easy way to correct for many of those possible assumptions. So here's a nice little table I put together a couple years back about how you might respond when you have different violations of assumptions. So bootstrapping, you'll notice, pops up a lot. So if you have heteroscedasticity in your model, bootstrapping is a good solution. Non-normality of residuals, bootstrapping, and outliers, bootstrapping. So bootstrapping is a good go-to. If you have multicollinearity, I just talked about this a couple slides ago, it's actually probably better just to get rid of whatever the problem variable is and rerun. That's going to be a lot easier, and bootstrapping is not going to fix that. If you have a regression outlier, you could also remove that outlier and rerun your results. That's fine. If you have evidence of nonlinearity, that's more a time to stop and ponder. What am I missing? Am I missing some kind of nonlinear effect, some squared or quadratic effect I need to put in? Do I need to transform my outcome? Should I take the log of my outcome? Should I change my model? So nonlinearity is kind of like a stop and ponder type assumption violation, but the others can be relatively easily fixed using a few simple techniques. So what is bootstrapping? Such a goofy name, right? It is a resampling technique. It's very intensive, and so it's great that we have fast computers. You can apply it to correcting for violated regression assumptions. It's really good for non-normality of residuals and heteroscedasticity. What's amazing is virtually anything you do can be bootstrapped. You can bootstrap a t-test, you can bootstrap a correlation, you can bootstrap a regression model, you can bootstrap an ANOVA. But we'll do it with regression now, and then later on we'll use it when we talk about mediation analysis. So basically, what is bootstrapping? Well, bootstrapping is basically taking the concept behind a sample, right, a simple random sample, and just applying it in a really unique way. So when anytime we talk about sampling from a population, right, the idea is, okay, there's this population out there and there's this unknown value, we'll call it a mean, that we want to figure out. And the way to figure it out is you just take a bunch of samples from that population and you get estimates of that mean. And over time, as you do this over and over, you're going to end up with a sampling distribution, right? Different values of that mean. In the middle of that distribution, the mean or the median, if it's normally distributed, that is going to get you as close as possible to the true population value. So that's the concept behind sampling, right? And this idea of a sampling distribution of a statistic. that we're interested in. And this all comes from a pretty cool piece by Tim Hesterberg, who's now at Google, but was interested in a lot of these things back then. So what is bootstrapping? Well, the idea is we can actually sort of simulate that same process of drawing from a population repeated samples. And as long as we do it enough, relying on this concept known as the central limit theorem, we can actually construct a sampling distribution for our standard errors that is more accurate. We can actually recover what's close to the true population standard errors by repeating this process. And so what you do is, you have, in this case, we've drawn one sample, one simple random sample of size n. But what you can do is you can resample that same little sample over and over, and you can get a bootstrap distribution. So you're essentially sort of artificially creating the sampling distribution and correcting for possible violations of assumptions. So what that means is, okay, let's say this sample is 50 people. Well, we're going to resample it with replacement, one sample of 50. Then we're going to redraw from that same sample with replacement, so the same person can be in there twice, another sample of 50. And you might do that 500 or 1,000 times. Again, this happens really fast using modern computers. And in doing so, we end up with this really cool bootstrap distribution, which ends up being much more accurate. So this is just another visual from Seb Rashka about this process. So here, let's say your original data set has 10 participants. I know these are X's, but let's assume they're people. To draw a bootstrap sample here, we're going to sample with replacement. So notice, in sample 1, X2 is actually represented twice. X8 is actually represented 3 times. That's okay, right? Sample 2, we're doing the same thing. Sample 3, you might do that 1,000 times. So you're going to resample that same sample 1,000 times and kind of aggregate all the results together. And so you could create 100 or 1,000 simulated data sets, and you're basically pretending that your sample is the population, and you're simulating the kind of trying to back out what the population parameters were from that. And then you can get these confidence intervals. So we'll talk about how to interpret all that when we get into this data in our demonstrations. So that's bootstrapping. It's really cool, really computer intensive, but with our kind of fast computers that we have now, it's not too onerous a process at all. So hopefully that was helpful. That is my end of my lecture on assumptions. Phew, we made it. Hopefully you found it helpful, and we'll dive into the demonstrations next. Thanks.